Alright, we're back again. This is a requested homework problem. I'm not sure what number it is because the number I was told it was doesn't exist in Chapter 5's homework problems. But you'll probably recognize it because it's in your homework. So this one is about an arrow being shot by an archer. The arrow weighs 0.024 kg and it is going to hit a target. The second it hits that target, its velocity is going to be decreasing until it tends towards zero. That will create an acceleration, a negative acceleration, or a deceleration. And so the tricky part of this problem is that it looks like a kinematics problem. It will function like a kinematics problem, but when we include this force stuff into it, it seems a little odd. Because one of the key assumptions here is, let's say that this is my bow and arrow, and I shoot my arrow. One of the key assumptions here is that the V initial of 54 meters per second is all in the x direction. And what that means is that even though this trajectory may drop due to gravity, if it's occurring on Earth, this arrow will always have the same 54 meters per second in the x direction. Because there's no acceleration in the x direction, the velocity in the x direction just continues as if nothing is happening. And so, with that assumption, the second assumption is similar, is that when it reaches the target, it's still going at 54 meters per second. And that it's going to penetrate the target and stop to 0 meters per second. So what I've done is I have drawn a zoomed in view. Hopefully you can see the red marker. I have just extended the target width so that we can look at this kind of minute width, because this is where the whole problem will happen. So this is our drawing. This is the entrance into the target, and this is the point at which the penetration ceases to occur and the velocity final is 0. So the distance between those 2 points I'm going to call delta x, and it's the penetration depth of 0.083 meters. Alright, and so now what we're going to do is kind of ignore this setup, and we're just going to write some equations, equations of motion. The first thing to realize is that we're looking for F average, and we know that F equals ma. And for constant acceleration, we can just plug in acceleration here and it'll spit out the average force that the target exerts on the arrow. Alright, so we know we have mass, we know we're looking for force, and can we solve for A? And so that's where we're looking next. We're trying to solve for A. Well, this problem doesn't give us time, so we should probably steer clear of any problems or any equations of motion that have to do with time. So out of the 4 equations of motions that I use, the one that pops up the most when I'm not given time and I'm not looking for time is this one. 2 times acceleration times the displacement equals v final squared minus v initial squared. Alright, so what do we know in here? Well, we know delta x, we know v final, although we haven't quite talked about that yet. We definitely know v initial. We know that by the time the penetration ceases to continue, the velocity of the arrow must be 0. Therefore, this term goes to 0. Now we can go ahead and solve for A. So we know that acceleration equals v initial squared minus v initial squared, right? Divide by 2 delta x. And we know both of these numbers. So this is minus 54 squared. Divide by 2 times the penetration depth, which is 0.083 meters. And now it's time to plug and chug. There's the calculator. So 54 squared divided by 2 divided by 0.083 gives us the acceleration, and the acceleration is now calculated to be approximately negative 17,566.3 meters per second squared. And of course the negative in front of this term represents that the acceleration is going in our negative, so we picked our coordinates to be positive right, negative left, and therefore the acceleration is occurring in this direction, and it's a decelerating acceleration. So that explains why it's negative. Now what we'll go ahead and do is we're going to go ahead and plug it into this master equation that we've been wanting to solve for force average. So in order to do that, it's just a plug and chug now. The hardest part of the problem is the assumptions at the beginning. So we know our mass. Mass is 0.024 kg. We know our acceleration is negative 17,566.3, and that's going to give us our F average, which is what we're looking for. So we go ahead and plug it in. 17,566.3 times 0.024. This yields a negative 421.6 newtons. Okay, and how do we interpret this negative? Well, once again, force is a vector quantity, so it's telling us in which direction the force points with respect to our convention that we chose. And it does make sense that if F equals ma, if the acceleration is this way, then also F will be this way as well, because F equals ma, right? And with that sort of, we can't have a negative mass, right? So if F equals ma and A is negative, likewise F will be negative. And if F is negative, likewise A will be negative. Now, don't think that this is like not a real force. Just like deceleration, it's a valid part of acceleration. Likewise, a negative force, it's not telling you that you can produce a negative force. All it's telling you is you could produce this force in this direction. So just think of the negative as an orienting factor. But if you wanted to give F average as a non-vector quantity, sometimes you could write that as just F average without a vector sign, or more formally, two absolute value signs to represent the magnitude of F average. Then that would just be 421.6 newtons. And of course, you could rewrite this to be 0.4216 kilonewtons. So anyways, I hope this was helpful. These problems with force average get a little bit tricky because it's hard to tell where the kinematics ends and how do you carry your results from the kinematics into finding your force. So, yeah. Have a nice day. I'll see you next time.